What if the universe itself is younger than some of the stars we see shining in the night sky? It sounds impossible, right? Stars born before the universe. Yet, this is the mind-bending reality we're about to explore. Imagine gazing up at the heavens, only to realize that some of those ancient lights have been burning longer than the cosmos itself. How can this be? What does it mean for our understanding of time, space, and the very origins of existence? Today, we're diving into the mysteries of 30 stars that defy everything we thought we knew about the universe. These celestial anomalies challenge the very timeline of creation, leaving scientists and stargazers alike in awe. From stars that predate the Big Bang to ancient giants hiding in plain sight, each one holds secrets that could rewrite the story of the cosmos. So, if you're ready to unravel the enigma of stars older than the universe itself, stay with us. By the end of this journey, you'll see the night sky in a whole new light and question everything you thought you knew about time and space. Let's begin. Now, let's turn our attention to the first star on our list, HD 140283, often called the Methuselah Star. This ancient celestial body has sparked both wonder and debate among astronomers, and for good reason. Located roughly 190 light-years away in the constellation Libra, this star is believed to be one of the oldest ever discovered. But here's where things get truly fascinating. Its estimated age is around 14.5 billion years. That's older than the universe itself, which is currently thought to be about 13.8 billion years old. How can a star be older than the universe? This paradox has left scientists scratching their heads and rethinking our understanding of cosmic timelines. The Methuselah Star was first identified in the early 20th century, but it wasn't until much later that its true significance came to light. Using advanced techniques like parallax measurements and spectroscopy, astronomers were able to determine its distance and composition. The star's low iron content was a key clue, as older stars tend to have fewer heavy elements which were formed later in the universe's history. By analyzing the star's brightness, temperature, and chemical makeup, researchers pieced together its age, leading to the startling conclusion that it might predate the cosmos itself. Of course, this discovery hasn't come without controversy. Some scientists argue that the star's age might be slightly overestimated due to uncertainties in the measurements or our understanding of stellar evolution. Others suggest that the universe's age might need reevaluation. Whatever the case, HD 140283 stands as a testament to the mysteries that still linger in the cosmos, challenging us to rethink what we know about time, space, and the origins of everything. As we move forward, this star serves as a reminder that the universe is far more complex and far older than we might have imagined. Now, let's dive deeper into the controversy surrounding the Methuselah Star's age. The idea that a star could be older than the universe itself is understandably a concept that challenges our fundamental understanding of cosmology. How can something exist before the very fabric of space and time? This paradox has led scientists to propose several theories to reconcile the star's age with the universe's timeline. One possibility is that the age estimate of HD 140283 might not be entirely accurate. While the methods used to determine its age are highly sophisticated, they still rely on certain assumptions about stellar evolution and the star's initial conditions. For instance, small errors in measuring the star's distance, brightness, or chemical composition could lead to significant discrepancies in its calculated age. Some researchers argue that if these measurements were slightly off, the star's age could align more closely with the universe's age, eliminating the paradox altogether. Another intriguing theory suggests that our understanding of the universe's age might need revisiting. The current estimate of 13.8 billion years is based on observations of the cosmic microwave background radiation and the rate of the universe's expansion. However, if there are gaps in our knowledge about dark energy, dark matter, or the early universe's conditions, it's possible that the universe itself is slightly older than we think. This would allow the Methuselah Star to fit more comfortably within the cosmic timeline. There's also the possibility that HD 140283 formed under unique conditions that we don't yet fully understand. For example, if the star was born in an environment with unusual chemical abundances or gravitational influences, it might have evolved in a way that makes it appear older than it truly is. This would mean that the star's age isn't a direct contradiction of the universe's age, but rather a reflection of its extraordinary origins. Despite these theories, the Methuselah Star remains a fascinating enigma, pushing scientists to refine their methods and question their assumptions. It's a reminder that the universe is full of surprises, and even our most well-established ideas can be challenged by a single, ancient star. As we continue to explore the cosmos, stars like HD 140283 will undoubtedly lead us to new discoveries and deeper questions about the nature of time, space, and existence itself. Next, we'll turn our attention to another ancient star that holds secrets of the early universe, shedding light on the first moments after the Big Bang. Now, let's journey even further back in time to uncover the secrets of another ancient star, SMSS J031300.36-670839.3. This star is a true relic of the early universe, believed to have formed just a few 100 million years after the Big Bang. Its existence offers us a rare glimpse into the conditions of the cosmos during its infancy, a time when the first stars were beginning to light up the darkness. What makes SMSS J031300.36-670839.3 so extraordinary is its chemical composition. Unlike most stars which contain traces of heavier elements like iron, this star is almost entirely made up of hydrogen and helium, the two simplest and most abundant elements in the early universe. This lack of heavier elements, often referred to as metals in astronomy, tells us that SMSS J031300.36-670839.3 likely formed from material that had not yet been enriched by the explosions of earlier stars. In other words, it's a second-generation star, born from the remnants of the very first stars that ever existed. The discovery of this star has been a game-changer for cosmologists. By studying its composition, scientists can piece together the story of how the first stars formed and died, seeding the universe with the heavier elements that would eventually make life possible. SMSS J031300.36-670839.3 is like a time capsule, preserving the chemical fingerprints of the universe's earliest days. Its existence challenges our understanding of stellar evolution and provides critical clues about the processes that shaped the cosmos in its first moments. As we continue to explore the mysteries of the early universe, stars like SMSS J031300.36-670839.3 remind us just how much there is still to learn. They push the boundaries of our knowledge and inspire us to keep looking deeper into the cosmos, searching for answers to the biggest questions about our origins. Next, we'll turn our attention to another ancient star that holds its own unique place in the story of the universe's beginnings. Now, shifting our focus to the broader implications, let's explore how SMSS J031300.36-670839.3 has reshaped our understanding of the early universe. This ancient star serves as a critical piece of the cosmic puzzle, offering a window into the era when the first stars ignited and began to transform the universe. Its unique composition, almost entirely devoid of iron and other heavier elements, tells a profound story about the conditions that existed billions of years ago. The absence of iron in SMSS J031300.36-670839.3 is particularly significant. Iron, along with other metals, is typically forged in the cores of massive stars and scattered into space during supernova explosions. The fact that this star contains so little iron suggests it formed from material that had not yet been enriched by these explosive events. This makes it a second-generation star, born from the remnants of the very first stars that ever existed. These first stars, often called population 3 stars, were massive and short-lived, composed almost entirely of hydrogen and helium. When they exploded, they seeded the universe with the first traces of heavier elements, setting the stage for the formation of stars like SMSS J031300.36-670839.3. By studying this star, scientists can infer the properties of those elusive first-generation stars. For instance, the lack of iron indicates that the first stars must have been incredibly massive, as only such stars could have produced the intense heat and pressure needed to create heavier elements. Their explosions would have been cataclysmic, scattering these elements across the cosmos and paving the way for the formation of subsequent generations of stars and planets. SMSS J031300.36-670839.3, therefore, acts as a bridge between the universe's earliest moments and the more complex structures we see today. Moreover, this star provides clues about the timeline of the early universe. Its age and composition suggest that the first stars formed relatively quickly after the Big Bang, within just a few 100 million years. This rapid formation challenges some existing models of cosmic evolution and pushes scientists to refine their understanding of how the universe transitioned from a dark, featureless void to one filled with light and structure. In essence, SMSS J031300.36-670839.3 is more than just an ancient star. It's a key to unlocking the secrets of the universe's infancy. Its existence reminds us that every star has a story to tell, and by listening to these stories, we can piece together the grand narrative of how everything we know came to be. As we move forward, we'll delve into another ancient star that holds its own unique place in this cosmic tale, further illuminating the mysteries of our universe's origins. Now, turning our gaze to another celestial marvel, let's explore He-152300901, a star that holds a special place in the annals of cosmic history. Nestled within the halo of our Milky Way galaxy, this ancient star is a treasure trove of information about the universe's earliest days. What makes He-152300901 truly remarkable is not just its age, but the groundbreaking methods scientists use to determine just how old it is. To uncover the age of He-152300901, researchers turn to a technique that might sound more at home in a geology lab than an astronomy observatory: radioactive decay measurements. Specifically, they analyzed the star's composition for traces of uranium and thorium, two elements that decay at predictable rates over billions of years. By measuring the amounts of these elements present in the star and comparing them to their decay products, scientists were able to calculate its age with remarkable precision. The results were astonishing. He-152300901 is estimated to be around 13.2 billion years old, making it one of the oldest stars ever discovered. But why is this star's age so significant? For one, it places He-152300901 among the first generation of stars to form after the Big Bang. Its ancient age offers a rare glimpse into the conditions of the early universe, a time when the cosmos was still in its infancy. The star's composition, rich in elements like uranium and thorium but lacking in heavier metals, further supports this timeline. These elements were likely forged in the explosive deaths of the very first stars, whose remnants seeded the universe with the building blocks for future generations of stars and planets. He-15230-901 also serves as a cosmic time capsule, preserving the chemical fingerprints of the universe's earliest moments. Its age and composition provide critical clues about how the first stars formed, lived, and died, shedding light on the processes that shaped the cosmos as we know it today. By studying stars like this, astronomers can piece together the story of how the universe evolved from a hot, dense soup of particles into the vast, structured expanse we observe today. As we continue our journey through the cosmos, He-15230-901 stands as a testament to the enduring mysteries of the universe. Its discovery not only deepens our understanding of stellar evolution, but also reminds us of the incredible resilience and longevity of the stars that light up our night sky. Next, we'll uncover the secrets of another ancient star, one that further illuminates the intricate tapestry of our universe's origins. Now, let's take a closer look at the fascinating science behind dating He-15230-901. The process of determining the age of such an ancient star is no small feat, and it relies on some of the most precise and innovative techniques in modern astronomy. At the heart of this method is the study of radioactive decay, specifically focusing on elements like uranium and thorium. These elements are like cosmic clocks, ticking away at a predictable rate over billions of years. By measuring the amounts of uranium and thorium present in the star and comparing them to their decay products, scientists can calculate how long these elements have been decaying and, by extension, how old the star itself is. But how exactly does this work? Uranium and thorium are both heavy elements that were likely formed in the explosive deaths of the very first stars, known as population 3 stars. When these ancient stars died, they scattered their remains across the cosmos, seeding the universe with the raw materials for future stars and planets. He-15230-901, being one of the earliest stars to form after this period, inherited these elements. Over time, the uranium and thorium within the star decayed into other elements at a steady rate, leaving behind a kind of chemical fingerprint. By analyzing the ratios of these elements and their decay products, astronomers can essentially read the star's age. This technique, known as nucleocosmology, is a powerful tool for understanding not just the age of individual stars but also the broader timeline of the universe. It's like piecing together a cosmic puzzle where each star provides a small but crucial piece of the picture. In the case of He-15230-901, the results were groundbreaking. The star's estimated age of 13.2 billion years places it among the oldest stars ever discovered, offering a rare window into the universe's earliest days. What makes this method so valuable is its ability to provide precise and reliable data. Unlike other dating techniques that rely on indirect evidence, radioactive decay measurements offer a direct way to estimate a star's age. This precision allows scientists to refine their understanding of stellar evolution and the timeline of cosmic events. For example, the age of He-15230-901 helps confirm that the first stars formed relatively quickly after the Big Bang, setting the stage for the universe as we know it today. As we continue to explore the cosmos, techniques like these will play a crucial role in unraveling the mysteries of stellar ages and the history of the universe. He-15230-901 is just one example of how the stars above can serve as both witnesses and storytellers, preserving the secrets of the past for us to uncover. Next, we'll turn our attention to another ancient star, one that further enriches our understanding of the universe's origins and the incredible journey of stellar evolution. Now, let's shift our gaze to another ancient marvel of the cosmos, BD plus 17°3248. This metal-poor star, nestled within the halo of our Milky Way galaxy, holds a special place in the study of the early universe. With an estimated age of around 13.5 billion years, BD plus 17 degrees 3248 is one of the oldest stars ever discovered, offering a glimpse into a time when the universe was still in its infancy. What makes this star particularly fascinating is its extremely low metal content. In astronomy, metals refer to any element heavier than hydrogen and helium, and the scarcity of these elements in BD plus 17 degrees 3248 tells us a lot about its origins. Stars like this one formed during a period when the universe was still relatively pristine, dominated by hydrogen and helium left over from the Big Bang. The lack of heavier elements suggests that BD plus 17 degrees 3248 is a second-generation star, born from the remnants of the very first stars that ever existed. Located approximately 2,000 light-years from Earth, this ancient star serves as a cosmic time capsule, preserving the chemical signature of the early universe. By studying its composition, astronomers can piece together the conditions that existed shortly after the Big Bang. For instance, the star's low metal content indicates that it formed before the universe had been significantly enriched by the explosive deaths of massive stars, which scattered heavier elements across the cosmos. BD plus 17 degrees 3248 also plays a crucial role in helping scientists understand the formation of the first stars, often referred to as population 3 stars. These primordial stars, which have never been directly observed, are thought to have been massive and short-lived, ending their lives in spectacular supernovae that seeded the universe with the first heavy elements. By studying stars like BD plus 17 degrees 3248, astronomers can infer the properties of these elusive population 3 stars and the processes that shaped the early universe. In many ways, BD plus 17 degrees 3248 is a bridge between the past and the present, connecting us to a time when the universe was young and the first stars were just beginning to light up the cosmos. Its existence challenges us to rethink our understanding of stellar evolution and the timeline of cosmic events. As we continue to explore the mysteries of the universe, stars like this one remind us of the incredible journey that has brought us to where we are today. Next, we'll delve into the unique chemical fingerprint of BD plus 17 degrees 3248 and what it reveals about the early stages of the universe. Now, let's take a closer look at the chemical fingerprint of BD plus 17 degrees 3248 and what it tells us about the early universe. This ancient star's composition is like a cosmic recipe book, revealing the ingredients and processes that shaped the universe in its earliest days. By analyzing its chemical makeup, scientists can uncover clues about how the first elements were forged and scattered across the cosmos. One of the most striking features of BD plus 17 degrees 3248 is its extremely low abundance of heavier elements such as iron and carbon. In fact, its iron content is less than 1/10,000th of that found in our Sun. This scarcity of metals points to a time when the universe was still young and had not yet been enriched by the explosions of massive stars. These explosions, known as supernova, are responsible for creating and dispersing heavier elements into space, which later become the building blocks for new stars and planets. The lack of these elements in BD plus 17 degrees 3248 suggests that it formed from material that had not yet been touched by such events. But the story doesn't end there. This star also contains trace amounts of elements like strontium and barium, which are produced through a process called the rapid neutron capture process, or R process. This process occurs during extreme cosmic events, such as the collision of neutron stars or certain types of supernova. The presence of these elements in BD plus 17 degrees 3248 hints that even in the early universe, such cataclysmic events were already taking place, seeding the cosmos with the first heavy elements. What's even more fascinating is that the chemical signature of BD plus 17 degrees 3248 aligns with predictions about the first generation of stars, known as population 3 stars. These stars, which have never been directly observed, are believed to have been massive and short-lived, ending their lives in powerful explosions that scattered the first heavy elements into the surrounding gas. BD plus 17°3248 as a second-generation star carries the chemical imprint of these primordial stars, offering a rare glimpse into their existence and the processes that shaped the early universe. By studying stars like BD plus 17°3248, astronomers can piece together the timeline of cosmic evolution. Its chemical fingerprint not only tells us about the conditions of the early universe, but also helps us understand how the first stars lived, died, and laid the foundation for everything that came after. As we continue to explore the cosmos, stars like this one serve as invaluable guides, helping us unravel the mysteries of our universe's origins. Next, we'll turn our attention to another ancient star, He0107-5240, and its role in understanding the first generation of stars. Now, shifting our gaze to another cosmic relic, let's explore He0107-5240, a star that stands as a testament to the universe's earliest days. This ancient star is one of the most metal-poor stars ever discovered, with a composition that offers a rare window into the conditions of the primordial cosmos. Its discovery in the early 2000s marked a significant milestone in our understanding of stellar evolution and the origins of the first stars. He0107-5240 is located in the halo of the Milky Way, a region populated by some of the oldest stars in our galaxy. What makes this star particularly fascinating is its extremely low abundance of heavy elements such as iron. In fact, its iron content is less than 1/200,000th of that found in our Sun. This scarcity of metals suggests that He0107-5240 formed from material that had not yet been enriched by the explosive deaths of massive stars, making it a potential descendant of the very first generation of stars, known as population 3 stars. Studying stars like He0107-5240 is no easy task. Their faintness and distance make them incredibly challenging to observe, requiring some of the most advanced telescopes and instruments available. Additionally, their unique chemical compositions demand precise measurements and careful analysis to unravel the secrets they hold. Despite these challenges, the insights gained from stars like this one are invaluable, as they help us piece together the story of how the first stars formed and how they shaped the universe we see today. One of the most intriguing aspects of He0107-5240 is its potential connection to the first stars. These population 3 stars, which have never been directly observed, are thought to have been massive and short-lived, ending their lives in spectacular supernovae that seeded the cosmos with the first heavy elements. He0107-5240, with its extremely low metal content, may carry the chemical signature of these ancient stars, offering clues about their properties and the processes that governed the early universe. As we continue to study stars like He0107-5240, we gain a deeper understanding of the universe's infancy. These ancient stars serve as cosmic time capsules, preserving the conditions and events of a time long before the formation of planets, galaxies, and even the elements that make up our world. By unlocking their secrets, we move closer to answering some of the most profound questions about the origins of the cosmos. Next, we'll delve into the mystery of how He0107-5240 formed in a universe that was almost entirely hydrogen and helium, and what it tells us about the early cosmos. Now, let's unravel the mystery of how He0107-5240 came to exist in a universe that was almost entirely hydrogen and helium. This ancient star's formation challenges our understanding of the early cosmos, offering a glimpse into a time when the universe was a vastly different place. One leading theory suggests that He0107-5240 formed from the remnants of the very first stars, known as population 3 stars. These stars, which have never been directly observed, are believed to have been massive and short-lived, composed almost entirely of hydrogen and helium. When they reached the end of their lives, they exploded in powerful supernova, scattering the first heavy elements into the surrounding space. He0107-5240, with its incredibly low metal content, may have formed from gas clouds that were only minimally enriched by these early supernova, preserving a nearly pristine chemical signature from the dawn of the universe. Another intriguing possibility is that this star formed in isolation, far from the influence of other stars. In the early universe, regions of space with lower densities of matter could have allowed pockets of gas to collapse and form stars without being contaminated by heavier elements. This would explain why He0107-5240 has such a unique composition, as it might have formed in one of these rare, undisturbed regions. The formation of stars like He0107-5240 also raises questions about the conditions of the early universe. For instance, how did these stars manage to form without the presence of heavier elements, which play a crucial role in cooling gas clouds and allowing them to collapse into stars today? Some scientists propose that the extreme temperatures and pressures of the early universe may have provided alternative mechanisms for star formation, allowing these ancient stars to take shape in ways that are fundamentally different from how stars form now. By studying He0107-5240, we gain valuable insights into the processes that shaped the first stars and the early cosmos. This star serves as a cosmic fossil, preserving the conditions of a time when the universe was young and uncharted. Its existence challenges us to rethink our understanding of star formation and the evolution of the universe itself. As we continue to explore the mysteries of He0107-5240, we move closer to uncovering the secrets of the universe's infancy. Next, we'll turn our attention to another ancient star, CS22892-052, and explore how its unusual composition sheds light on the origins of heavy elements in the cosmos. Now, let's shift our gaze to another cosmic marvel, CS22892-052, a star that stands out for its extraordinary composition. This ancient star is a treasure trove of R-process elements, which are heavy elements like gold, platinum, and uranium, forged in some of the most violent events in the universe. But what makes CS22892-052 so special, and what can it tell us about the early universe? CS22892-052 is estimated to be around 13 billion years old, making it one of the oldest stars ever discovered. Its age places it in the early stages of the universe, a time when the first stars and galaxies were just beginning to form. But what truly sets this star apart is its unusually high concentration of R-process elements. These elements are typically created in rare and extreme cosmic events, such as neutron star mergers or supernova, where the conditions are so intense that atomic nuclei can capture neutrons rapidly, forming heavier elements. The presence of these R-process elements in CS22892-052 suggests that such cataclysmic events occurred very early in the universe's history. This challenges our understanding of how quickly heavy elements were able to form and spread throughout the cosmos. It also raises fascinating questions about the environments in which the first stars and galaxies emerged. Were neutron star collisions more common in the early universe, or did supernova in those early days produce heavier elements more efficiently than they do today? By studying CS22892-052, scientists can piece together clues about the processes that seeded the universe with the building blocks of planets, life, and even us. This star acts as a cosmic time capsule, preserving the chemical fingerprints of the universe's infancy. Its unique composition not only sheds light on the origins of heavy elements, but also helps us understand how the universe evolved from a simple, primordial state into the complex and diverse cosmos we see today. As we continue to explore the mysteries of CS22892-052, we'll delve deeper into the R process and how this star's composition provides a window into the early universe. Next, we'll uncover the story of another ancient star, He1327-2326, and explore the challenges astronomers face when studying these faint relics of the cosmos. Now, let's take a closer look at the R process, or rapid neutron capture process, which plays a crucial role in shaping the chemical makeup of stars like CS22892-052. This process is one of the key mechanisms responsible for creating many of the heavy elements we see in the universe today, including gold, platinum, and uranium. But how does it work, and why is it so important to our understanding of cosmic history? The R process occurs in environments where there's an overwhelming abundance of free neutrons, such as during neutron-star collisions or certain types of supernova. In these extreme conditions, atomic nuclei are bombarded with neutrons at such a rapid pace that they can't decay into stable forms quickly enough. Instead, they capture multiple neutrons, forming heavier and heavier elements. Once the neutron flux subsides, these unstable nuclei undergo radioactive decay, eventually transforming into stable, heavy elements. This process is incredibly fast, hence the name, rapid neutron capture process, and it's responsible for producing about half of the heavy elements in the universe. What makes CS22892-052 so fascinating is its unusually high concentration of these R process elements. This suggests that the star formed from material that was enriched by one or more of these cataclysmic events very early in the universe's history. By studying the ratios of these elements in the star, scientists can trace back the conditions and events that created them. For example, the presence of certain isotopes can reveal whether the R process occurred in a neutron-star merger or a supernova, and even provide clues about the frequency of these events in the early cosmos. This star's composition is like a snapshot of the universe's chemical evolution. It tells us that heavy elements were being produced and distributed much earlier than we once thought, challenging the idea that the early universe was a simple, pristine environment. Instead, it was a dynamic and chaotic place where violent events shaped the building blocks of future stars, planets, and even life. CS22892-052 gives us a rare glimpse into this formative period, helping us piece together the story of how the universe went from a sea of hydrogen and helium to the rich, diverse cosmos we see today. As we continue to unravel the mysteries of the R process and its role in cosmic history, we'll turn our attention to another ancient star, He1327-2326, and explore the challenges astronomers face when studying these faint but incredibly important relics of the early universe. Now, shifting our gaze to another cosmic relic, we encounter He1327-2326, a star that stands out for its remarkably low iron content. This ancient star, located in the halo of our Milky Way, is a treasure trove of information about the early universe. Discovered in the early 2000s, He1327-2326 quickly caught the attention of astronomers due to its unusual chemical composition. Unlike most stars which contain traces of heavier elements like iron, this star is almost entirely devoid of them, making it one of the most iron-poor stars ever observed. The scarcity of iron in He1327-2326 is a direct clue to its age. Iron and other heavy elements are forged in the cores of massive stars and spread throughout the cosmos during supernova explosions. Since this star contains almost none of these elements, it likely formed from material that had not yet been enriched by such events. This places He1327-2326 among the first generation of stars, born in a universe that was still in its infancy. Its composition offers a rare glimpse into the conditions of the early cosmos, when the universe was dominated by hydrogen and helium, with only the faintest traces of heavier elements. But what makes this star truly fascinating is what its chemical makeup reveals about the processes at work in the early universe. The presence of certain light elements, such as carbon and oxygen, suggests that even in its earliest stages, the universe was already capable of producing some heavier elements through less violent processes, like fusion in the cores of smaller stars. This challenges the idea that the early universe was entirely devoid of complexity, hinting instead at a more nuanced and dynamic environment. Studying stars like He 1327-2326 is no easy task. These ancient stars are incredibly faint, and their light has traveled billions of years to reach us. Detecting and analyzing their spectra requires some of the most advanced telescopes and instruments available. Yet, despite these challenges, the insights gained from stars like this are invaluable. They help us piece together the story of how the first stars and galaxies formed, and how the universe evolved from a simple, primordial state into the complex and diverse cosmos we see today. As we continue our journey through the stars that defy our understanding of time and space, we'll next explore the challenges astronomers face when observing these faint but crucial relics of the early universe, and how technological advancements are helping us unlock their secrets. Now, let's turn our attention to the challenges astronomers face when studying stars like He 1327-2326. Observing these ancient, faint stars is no small feat. Their light is incredibly dim, having traveled across billions of years to reach us, and capturing enough of that light to analyze requires cutting-edge technology and precision. One of the biggest hurdles is the sheer distance and faintness of these stars. Unlike brighter, younger stars that dominate the night sky, He 1327-2326 is barely visible even with the most powerful telescopes. To detect its light, astronomers rely on instruments like the Very Large Telescope in Chile and the Hubble Space Telescope, which are equipped with highly sensitive detectors capable of picking up even the faintest signals. These tools allow scientists to gather the star's light and break it down into a spectrum, revealing the chemical fingerprints that tell us so much about its origins. But even with these advanced instruments, the process is far from straightforward. The faint light from He 1327-2326 is often drowned out by the glare of brighter stars or the glow of Earth's atmosphere. To overcome this, astronomers use techniques like adaptive optics, which correct for atmospheric distortions in real time, and long exposure times where the telescope collects light over hours or even days to build up a clear image. These methods help isolate the star's light from the surrounding noise, making it possible to study its composition in detail. Another challenge lies in interpreting the data. The spectra of ancient stars like He 1327-2326 are incredibly complex, with subtle features that require careful analysis. Scientists use sophisticated computer models to simulate the conditions of the early universe and compare them to the observed data. This helps them understand how the star formed and what its chemical makeup tells us about the environment in which it was born. Despite these challenges, the rewards of studying stars like He 1327-2326 are immense. Each observation brings us closer to understanding the universe's earliest moments and the processes that shaped its evolution. As technology continues to advance, astronomers are finding new ways to push the boundaries of what we can observe, unlocking the secrets of these ancient cosmic relics one star at a time. Next, we'll explore another fascinating star that sheds light on the early universe, revealing even more about the conditions that existed billions of years ago. Now, shifting our gaze to another cosmic marvel, let's explore SDSS J102915+172927, a star that stands out for its astonishingly low metal content. This ancient star, located in the constellation Leo, is a window into the universe's infancy, offering clues about the conditions that existed shortly after the Big Bang. What makes SDSS J102915+172927 so remarkable is its composition. It contains almost no metals, a term astronomers use to describe elements heavier than hydrogen and helium. This scarcity of metals is a telltale sign that this star formed in a nearly pristine environment, one that had not yet been enriched by the explosive deaths of earlier stars. The age of SDSS J102915+172927 is estimated to be around 13 billion years, placing it among the oldest stars ever discovered. Its existence challenges our understanding of star formation in the early universe. According to current theories, the first stars, often called population 3 stars, were composed almost entirely of hydrogen and helium with no heavier elements. While SDSS J102915+172927 isn't a population 3 star itself, its extremely low metal content suggests it formed from material that was only slightly enriched by the first generation of stars. This makes it a crucial link in the chain of cosmic evolution, helping us piece together how the universe transitioned from its simple beginnings to the complex, metal-rich environment we see today. Studying stars like SDSS J102915+172927 is no easy task. Their faintness and distance make them difficult to observe, but the insights they provide are invaluable. By analyzing the light from this star, astronomers can infer the conditions of the early universe, such as the temperature, density, and chemical composition of the gas clouds from which it formed. These observations help refine our models of the Big Bang and the processes that shaped the cosmos in its earliest moments. What's truly fascinating is how SDSS J102915+172927 challenges our assumptions about star formation. Conventional wisdom suggests that stars need at least some metals to form, as these elements help cool the gas clouds, allowing them to collapse and ignite. Yet, this star's existence hints that even in a nearly metal-free environment, stars could still form, albeit under different conditions. This discovery opens up new questions about the diversity of star formation mechanisms in the early universe and how the first stars might have differed from those we see today. As we continue to uncover the secrets of stars like SDSS J102915+172927, we gain a deeper appreciation for the complexity and wonder of the cosmos. Each discovery brings us closer to understanding how the universe evolved from a hot, dense state to the vast, intricate tapestry of stars, galaxies, and planets we observe today. Next, we'll delve into another ancient star that holds its own unique story, shedding even more light on the universe's earliest chapters. Now, let's take a closer look at how SDSS J102915+172927 came to be. The formation of this ancient star is a puzzle that challenges our understanding of the early universe. In a cosmos dominated by hydrogen and helium with almost no heavier elements, the process of star formation would have been vastly different from what we observe today. Without metals to cool the gas clouds, the conditions for star birth would have been far more extreme, requiring higher temperatures and densities for collapse to occur. One leading theory suggests that the first stars, often referred to as population 3 stars, were massive and short-lived, burning through their fuel quickly and ending their lives in spectacular supernova. These explosions would have seeded the surrounding gas clouds with the first traces of heavier elements, creating the slightly enriched environment from which stars like SDSS J102915+172927 could form. While this star isn't a population 3 star itself, its extremely low metal content indicates it formed from material that had only been minimally influenced by these early cosmic events. This makes it a critical piece of evidence in understanding how the universe transitioned from its primordial state to the more chemically diverse cosmos we see today. Another intriguing possibility is that SDSS J102915+172927 formed in a region of the universe that remained relatively untouched by the first supernova. This could explain its remarkably low metal content, as it would have formed from gas that had not yet been significantly enriched by heavier elements. Such a scenario would require specific conditions, such as isolated pockets of pristine gas that somehow avoided contamination from nearby star-forming regions. This idea opens up new questions about the distribution of matter in the early universe and how some regions could remain chemically pristine for so long. The formation of stars like SDSS J102915+172927 also raises questions about the role of dark matter in the early universe. Some scientists propose that dark matter played a crucial role in the formation of the first stars and galaxies, providing the gravitational scaffolding needed to pull together the sparse gas clouds. If this is true, then stars like SDSS J102915+172927 might owe their existence, at least in part, to the influence of dark matter in the early cosmos. What's clear is that SDSS J102915+172927 offers a rare glimpse into a time when the universe was still in its infancy. Its formation challenges our assumptions about how stars can form and survive in environments that seem inhospitable by today's standards. By studying this star, astronomers are not only learning about its origins, but also piecing together the broader story of how the universe evolved from simplicity to complexity. As we move forward, we'll explore another ancient star that holds its own unique secrets, further illuminating the mysteries of the early universe. Each discovery brings us closer to understanding the cosmic processes that shaped everything we see today. Now, let's turn our attention to another remarkable relic of the early cosmos, J02330343. This ancient star, nestled within the halo of our Milky Way galaxy, offers a unique window into the universe's formative years. With an estimated age of around 13 billion years, J02330343 is one of the oldest stars ever discovered, making it a key piece of the puzzle in understanding how the universe evolved from its primordial beginnings. Located approximately 7,000 light-years from Earth, J02330343 is part of a population of stars known as Population 2 stars. These stars are characterized by their low metal content, a telltale sign that they formed early in the universe's history, before successive generations of stars had enriched the cosmos with heavier elements. The scarcity of metals in J02330343 suggests it formed from material that had only been minimally processed by previous stellar generations, offering a glimpse into the chemical makeup of the early universe. To determine the age and composition of J02330343, astronomers rely on a combination of spectroscopic analysis and stellar modeling. By studying the star's light, scientists can identify the presence of specific elements in its atmosphere, such as iron, carbon, and oxygen. The relative abundance of these elements provides clues about the star's origins and the environment in which it formed. Additionally, stellar models help estimate the star's age by comparing its observed properties, such as temperature and luminosity, with theoretical predictions of how stars evolve over time. One of the most intriguing aspects of J02330343 is its role in helping us understand the timeline of the early universe. By studying stars like this, astronomers can piece together the sequence of events that followed the Big Bang, from the formation of the first stars and galaxies to the gradual enrichment of the cosmos with heavier elements. J02330343 serves as a cosmic time capsule, preserving information about the conditions that existed billions of years ago. As we continue to explore the mysteries of the early universe, stars like J02230033 remind us of the incredible complexity and beauty of the cosmos. Each discovery brings us closer to understanding how the universe transformed from a sea of simple elements into the rich tapestry of stars, galaxies, and planets we see today. Next, we'll delve into another ancient star that holds its own unique secrets, further illuminating the story of our cosmic origins. Now, let's take a closer look at how J02230033 plays a pivotal role in the fascinating field of stellar archaeology. This ancient star is like a cosmic historian holding clues to the universe's earliest chapters. By studying its composition and age, scientists can reconstruct the conditions that existed shortly after the Big Bang, offering a rare glimpse into the infancy of our cosmos. Stellar archaeology, sometimes referred to as galactic archaeology, focuses on uncovering the history of the universe by examining its oldest stars. These stars act as time capsules, preserving the chemical fingerprints of the early universe. J02230033, with its remarkably low metal content, is a prime example of a star that formed when the universe was still in its youth. Its composition reflects the primordial material from which it was born, providing invaluable insights into the processes that shaped the cosmos in its earliest stages. One of the key contributions of J02230033 to stellar archaeology lies in its ability to help scientists trace the origins of the elements. In the early universe, only the lightest elements, hydrogen, helium, and trace amounts of lithium, existed. Heavier elements like carbon, oxygen, and iron were forged later in the hearts of stars and scattered across the cosmos through supernova explosions. The scarcity of these heavier elements in J02230033 suggests it formed before many of these supernovae had occurred, making it a living relic of a simpler, more pristine cosmic era. Moreover, the study of stars like J02230033 allows astronomers to test and refine their models of stellar evolution and nucleosynthesis. By comparing the observed properties of this star with theoretical predictions, scientists can better understand how the first stars formed, lived, and died. This, in turn, helps piece together the timeline of cosmic evolution, from the birth of the first stars to the formation of galaxies like our own Milky Way. J02230033 also sheds light on the role of population 2 stars in the broader context of galactic history. These ancient stars, found primarily in the halos of galaxies, are thought to be remnants of the earliest structures that formed in the universe. By studying their distribution and properties, astronomers can gain a deeper understanding of how galaxies assembled and evolved over billions of years. In essence, J02230033 is more than just an ancient star. It's a key to unlocking the secrets of the universe's infancy. Its existence reminds us that the cosmos is a dynamic, ever-changing place, and that by studying its oldest inhabitants, we can uncover the story of how everything we see today came to be. As we move forward, we'll explore another ancient star that holds its own unique place in the cosmic narrative, further enriching our understanding of the universe's origins. Now, let's turn our attention to another remarkable cosmic relic, BPS CS310820001. This ancient star stands out not just for its age, but for its unusually high uranium content, which makes it a treasure trove for scientists studying the early universe. BPS CS310820001 is one of the oldest stars ever discovered, with an estimated age of around 13 billion years. To put that into perspective, this star formed when the universe was still in its infancy, just a few 100 million years after the Big Bang. Its age alone makes it a fascinating object of study, but what truly sets it apart is its chemical composition. Unlike many other ancient stars, BPS CS310820001 contains significant amounts of uranium, a heavy element that is rarely found in such abundance in stars of this age. The presence of uranium in BPS CS310820001 is particularly intriguing because uranium is formed through a process called the R process, or rapid neutron capture process. This process occurs during some of the most violent events in the universe, such as supernova explosions or neutron star mergers. The fact that this star contains uranium suggests that these cataclysmic events were already taking place in the early universe, seeding the cosmos with heavy elements long before the formation of planets like Earth. By studying the uranium content in BPS CS310820001, scientists can gain valuable insights into the timeline of nucleosynthesis, the creation of elements in the universe. Uranium decays at a known rate, and by measuring the amount of uranium remaining in the star, researchers can estimate how long ago it was formed. This, in turn, helps refine our understanding of when the first heavy elements were produced and how they were distributed throughout the cosmos. But the significance of BPS CS310820001 goes beyond just uranium. Its overall chemical makeup provides a snapshot of the conditions in the early universe. Like other ancient stars, it has very low levels of heavier elements like iron, indicating that it formed before many of the supernovae that enriched the universe with these materials. This makes it a crucial piece of the puzzle in understanding how the first stars and galaxies came to be. In essence, BPS CS310820001 is more than just an ancient star. It's a cosmic time capsule that helps us piece together the story of the universe's earliest moments. Its uranium content offers a rare glimpse into the processes that shape the cosmos, while its age and composition provide critical clues about the formation of the first stars and the evolution of the elements. As we continue our journey through the cosmos, we'll explore yet another ancient star that holds its own unique secrets, further deepening our understanding of the universe's origins. Now, let's take a closer look at how scientists use uranium dating to unlock the secrets of BPS CS310820001 and what this tells us about the universe's timeline. Uranium dating is a powerful tool in astronomy, allowing researchers to estimate the age of stars by measuring the decay of uranium isotopes. This method works because uranium decays at a predictable rate, transforming into other elements over time. By analyzing the amount of uranium remaining in BPS CS310820001, scientists can calculate how long ago the star formed, giving us a window into the early universe. The process begins with spectroscopy, a technique that allows astronomers to study the light emitted by stars. By breaking down this light into its component colors, scientists can identify the chemical elements present in the star. In the case of BPS CS310820001, the detection of uranium was a groundbreaking discovery. This heavy element formed through the R process provides a unique clock for dating the star. Since uranium decays into lead over billions of years, the ratio of uranium to lead in the star's atmosphere offers a direct measure of its age. What makes uranium dating particularly fascinating is its ability to reveal not just the age of the star, but also the timeline of nucleosynthesis, the process by which elements are created. The presence of uranium in BPS CS310820001 suggests that the R process was already active in the universe's early stages, producing heavy elements like uranium within the first few 100 million years after the Big Bang. This challenges earlier assumptions about how quickly the universe became enriched with heavy elements and provides critical insights into the conditions of the early cosmos. Moreover, uranium dating helps refine our understanding of stellar evolution. By comparing the ages of ancient stars like BPS CS310820001 with other cosmic objects, scientists can piece together a more accurate timeline of the universe's history. This star, with its uranium-rich composition, acts as a cosmic benchmark, helping us understand when and how the first heavy elements were forged and distributed across the universe. As we continue to explore the mysteries of the cosmos, stars like BPS CS310820001 remind us of the incredible precision and ingenuity of modern astronomy. Through techniques like uranium dating, we're not just uncovering the ages of stars, we're unraveling the story of the universe itself. Next, we'll turn our attention to another ancient star, He12190312, and discover what its unique chemical makeup reveals about the early universe. Now, shifting our gaze to another cosmic relic, let's explore the fascinating story of He12190312, a star that offers a unique glimpse into the universe's infancy. Discovered in the early 2000s, this ancient star stands out for its remarkably low metal content, a characteristic that places it among the earliest generations of stars to form after the Big Bang. Its scarcity of heavy elements like iron and carbon makes it a rare and invaluable window into the conditions of the early cosmos. Studying stars like He12190312 is no small feat. These ancient objects are incredibly faint, often hidden in the vast expanse of the Milky Way's halo. Detecting their light requires some of the most advanced telescopes and instruments available, such as the European Southern Observatory's Very Large Telescope. Even with these tools, the process is painstaking, as astronomers must sift through vast amounts of data to identify the subtle signatures of these ancient stars. The challenge is compounded by the fact that these stars are not only dim but also incredibly rare, making their discovery a true triumph of modern astronomy. What makes He12190312 particularly significant is its chemical composition. Unlike younger stars, which are enriched with heavier elements forged in previous generations of stars, this ancient star contains almost no metals. This lack of heavy elements suggests that it formed from nearly pristine material, composed almost entirely of hydrogen and helium, the elements created in the Big Bang. By studying its composition, scientists can piece together the conditions of the early universe and better understand how the first stars and galaxies came into being. However, the challenges don't end with detection. Analyzing the light from He12190312 requires precise measurements and sophisticated models to interpret its spectrum. Even the smallest errors in data collection or analysis can lead to significant uncertainties in determining the star's age and composition. Despite these hurdles, the insights gained from stars like He12190312 are invaluable, helping us refine our understanding of stellar evolution and the timeline of the universe's formation. As we continue to uncover the secrets of these ancient stars, each discovery brings us closer to answering some of the most profound questions about our cosmic origins. He12190312, with its metal-poor composition and ancient light, serves as a reminder of the universe's humble beginnings and the incredible journey it has taken to reach the state we see today. Next, we'll turn our attention to another ancient star, He01084743, and explore its role in shaping our understanding of the early universe. Now, let's take a closer look at the chemical composition of He12190312 and what it reveals about the universe's earliest moments. This ancient star is a treasure trove of information, not because of what it contains, but because of what it lacks. Its near absence of heavy elements like iron and carbon is a direct clue to its origins, pointing to a time when the universe was still in its infancy, filled with only the simplest elements, hydrogen and helium. The chemical makeup of He12190312 is like a cosmic fingerprint, preserving the conditions of the universe as it was over 13 billion years ago. Unlike younger stars, which are enriched with metals forged in the hearts of earlier stellar generations, this star's composition is almost entirely pristine. This suggests it formed from material that had not yet been processed by previous stars, offering a rare glimpse into the universe's primordial state. By studying its spectrum, scientists can trace the origins of the elements we see today and better understand how the first stars and galaxies came to be. One of the most striking features of He121903112 is its extremely low metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. In this star's case, the metallicity is so low that it's almost undetectable, making it one of the most metal-poor stars ever discovered. This scarcity of heavy elements is a hallmark of the first generation of stars, which formed before supernova could scatter metals across the cosmos. By analyzing its composition, researchers can piece together the processes that shaped the early universe and set the stage for the formation of more complex structures. But the story doesn't end there. The presence of trace amounts of certain elements in He121903112 also provides clues about the environment in which it formed. For example, the detection of lithium in its spectrum is particularly intriguing. Lithium is one of the few elements produced in significant quantities during the Big Bang, and its presence in this star supports theories about the conditions of the early universe. However, the amount of lithium observed in He121903112 is lower than predicted by some models, raising new questions about the processes that govern the universe's chemical evolution. The study of stars like He121903112 is not just about understanding the past, it's also about refining our models of stellar and cosmic evolution. Each discovery helps scientists test and improve their theories, bringing us closer to a complete picture of how the universe evolved from a hot, dense state to the complex, star-filled expanse we see today. As we continue to explore the chemical fingerprints of these ancient stars, we uncover new layers of the universe's history, one element at a time. Next, we'll turn our attention to another ancient star, He01084743, and delve into its role in shaping our understanding of the early cosmos. Now let's journey to another ancient relic of the cosmos, He01084743. This star, much like the ones we've explored so far, holds a special place in the story of the universe's earliest days. Located in the halo of our Milky Way galaxy, He01084743 is a window into a time when the universe was young and the first stars were just beginning to ignite. Its age, estimated to be over 13 billion years, places it among the oldest stars ever discovered, making it a key piece of the puzzle in understanding how the first generation of stars came to be. What makes He01084743 particularly fascinating is its role in the field of stellar archaeology. This branch of astronomy focuses on studying ancient stars to uncover the history of the universe, much like how archaeologists study artifacts to learn about ancient civilizations. By examining the chemical composition of stars like He01084743, scientists can trace the origins of the elements that make up everything around us, from the planets to the stars themselves. This star's near-pristine composition, with almost no heavy elements, suggests it formed from material that had not yet been enriched by the explosions of earlier stars. This makes it a rare and valuable snapshot of the universe's infancy. The location of He01084743 in the Milky Way's halo is also significant. The halo is a sparse, spherical region surrounding the galaxy, home to some of the oldest stars in existence. Unlike stars in the galaxy's disk, which are often younger and richer in metals, halo stars like He01084743 have remained relatively untouched by the processes that shape the more crowded regions of the galaxy. This isolation has preserved their ancient characteristics, allowing astronomers to study them as they were billions of years ago. One of the most intriguing aspects of He 0108473 is its extremely low metallicity. Like other first-generation stars, it contains almost no elements heavier than hydrogen and helium, a telltale sign of its ancient origins. This lack of metals provides critical evidence for theories about the early universe, suggesting that the first stars formed in an environment where heavy elements were virtually non-existent. By studying stars like this, scientists can refine their models of how the first stars and galaxies formed, shedding light on the processes that shaped the cosmos as we know it today. As we continue to explore the mysteries of He 0108473 and other ancient stars, we gain a deeper understanding of the universe's origins. Each discovery brings us closer to answering fundamental questions about how the first stars ignited, how galaxies formed, and how the elements essential for life came to be. Next, we'll turn our attention to another ancient star, He 012303343, and uncover its unique contributions to our understanding of the early universe. Now, let's delve deeper into the formation of He 0108473 and what it tells us about the early universe. This ancient star, with its remarkably low metal content, offers a rare glimpse into a time when the cosmos was still in its infancy. The prevailing theory suggests that stars like He 0108473 formed from clouds of gas that were almost entirely composed of hydrogen and helium, the simplest and most abundant elements in the early universe. These primordial clouds lacked the heavier elements or metals that we see in younger stars today, because those elements had not yet been forged in the hearts of earlier stars or scattered by their explosive deaths. The formation of such stars is thought to have been a very different process compared to the birth of stars in the modern universe. Without metals to help cool the gas clouds, the first stars likely formed in much larger and more massive clumps. This is because metals play a crucial role in allowing gas to cool and condense into smaller, denser regions, which then collapse to form stars. In the absence of these cooling agents, the gas clouds would have remained hotter and more diffuse, leading to the formation of fewer but much more massive stars. He 0108473, however, appears to be an exception to this rule. Its relatively low mass suggests that it may have formed under slightly different conditions, possibly in a region where the gas was able to cool and fragment more effectively, even without the presence of metals. This unique formation process provides valuable clues about the environment of the early universe. The fact that He 0108473 exists at all challenges some of our assumptions about how the first stars formed. It suggests that there may have been pockets of the early universe where gas could cool and collapse into smaller stars, even without the help of metals. This could mean that the first generation of stars was more diverse than we once thought, with a mix of both massive and smaller stars. By studying stars like He 0108473, astronomers can refine their models of star formation in the early universe, helping us better understand the conditions that gave rise to the first stars and galaxies. Another fascinating aspect of He 0108473's formation is what it reveals about the chemical evolution of the universe. The near absence of metals in this star indicates that it formed before the first supernova had a chance to enrich the surrounding gas with heavier elements. This makes it a living fossil, preserving the chemical signature of the universe as it was just after the Big Bang. By analyzing its composition, scientists can piece together the timeline of when the first stars began to produce and distribute metals, marking the beginning of the chemical complexity that would eventually lead to the formation of planets, life, and everything we see around us today. As we continue to study stars like He 0108473, we uncover more about the intricate processes that shaped the early universe. Each discovery brings us closer to understanding how the first stars ignited, how they influenced their surroundings, and how they set the stage for the rich and diverse cosmos we inhabit today. Next, we'll explore another ancient star, J01230343, and uncover the secrets it holds about the universe's earliest days. Now, shifting our gaze to another cosmic relic, let's explore the intriguing story of J13201339. This ancient star, nestled within the halo of our Milky Way, offers yet another window into the universe's earliest moments. Like the stars we've discussed before, J13201339 stands out for its remarkably low metal content, a telltale sign that it formed during a time when the cosmos was still in its infancy. Its age, estimated to be around 13 billion years, places it among the oldest stars ever discovered, making it a key piece of the puzzle in understanding the universe's formative years. Located approximately 4,000 light-years from Earth, J13201339 resides in a region of the galaxy known as the Halo, a sparse and ancient collection of stars that surrounds the Milky Way's more densely populated disk. This location is significant because stars in the halo are typically older and less chemically enriched than those in the disk, providing a clearer snapshot of the early universe. The halo stars, including J13201339, are like time capsules preserving the conditions and elements of a much younger cosmos. To determine the age of J13201339, astronomers rely on a combination of techniques, including spectroscopy and radioactive decay measurements. Spectroscopy allows scientists to analyze the star's light, breaking it down into its component colors to reveal the presence of specific elements. In the case of J13201339, the near absence of heavier elements like iron and the presence of lighter elements such as hydrogen and helium confirm its ancient origins. Additionally, radioactive decay measurements of elements like uranium and thorium provide a more precise estimate of the star's age, as these elements decay at known rates over billions of years. What makes J13201339 particularly fascinating is its role in helping us understand the timeline of the early universe. By studying its composition and age, scientists can piece together the sequence of events that followed the Big Bang, such as when the first stars ignited and how they began to enrich the cosmos with heavier elements. This star's existence challenges some of our assumptions about the early universe, suggesting that even in its earliest stages, the cosmos was capable of producing a diverse array of stars with varying sizes and compositions. As we continue to unravel the mysteries of stars like J13201339, we gain a deeper appreciation for the complexity and beauty of the universe's beginnings. Each discovery brings us closer to understanding how the first stars shaped the cosmos, setting the stage for the galaxies, planets, and life that would follow. Next, we'll turn our attention to another ancient star, J14240241, and uncover the secrets it holds about the universe's earliest days. Now, let's delve deeper into the significance of J13201339 and how it shapes our understanding of the cosmos. This ancient star isn't just a relic of the past, it's a key player in the story of how the universe evolved. By studying its unique properties, scientists can piece together the conditions that existed shortly after the Big Bang, shedding light on the formation of the very first stars. One of the most critical contributions of J13201339 lies in its chemical composition. The star's near absence of heavier elements like iron and its abundance of lighter elements such as hydrogen and helium provide a snapshot of the universe before it became enriched with metals. This tells us that J13201339 likely formed from material that had not yet been processed by earlier generations of stars. In other words, it's a direct link to the primordial gas clouds that existed in the universe's infancy. This star also helps astronomers refine their models of stellar evolution. By comparing its properties to those of younger stars, researchers can better understand how the first stars formed, lived, and died. For instance, the lack of metals in He-13201339 suggests that the earliest stars were massive and short-lived, exploding as supernova and scattering heavier elements into space. These elements would later become the building blocks for subsequent generations of stars, planets, and even life itself. Moreover, He-13201339 offers clues about the timeline of the early universe. Its age, estimated at around 13 billion years, places it among the oldest stars ever discovered. This means it formed relatively soon after the Big Bang, providing a benchmark for when the first stars began to illuminate the cosmos. By studying stars like this, scientists can better estimate when the universe transitioned from a dark, featureless void to one filled with light and structure. Another fascinating aspect of He-13201339 is its location in the Milky Way's halo. Stars in this region are typically older and less chemically enriched than those in the galaxy's disk, making them invaluable for studying the early universe. The halo acts as a cosmic archive, preserving stars that formed when the universe was still in its youth. He-13201339, as a member of this ancient population, helps us understand how the Milky Way itself came to be, offering insights into the processes that shaped our galaxy over billions of years. In essence, He-13201339 is more than just an ancient star. It's a window into the universe's formative years. Its existence challenges our understanding of the early cosmos, pushing us to refine our theories and explore new questions. As we continue to study stars like this, we gain a clearer picture of how the universe evolved from its chaotic beginnings to the complex, beautiful structure we see today. Next, we'll turn our attention to another ancient star, He-14240241, and uncover the secrets it holds about the universe's earliest days. Now let's shift our gaze to another cosmic time capsule, He-14240241. This ancient star, much like the ones we've explored so far, holds secrets from the universe's earliest days. Discovered in the Milky Way's halo, He-14240241 stands out for its remarkably low metal content, making it a crucial piece of the puzzle in understanding the conditions of the early cosmos. The discovery of He-14240241 was no small feat. Detecting such faint, ancient stars requires cutting-edge telescopes and precise observational techniques. Its light, traveling across billions of years, carries with it a wealth of information about the universe's infancy. But studying stars like this isn't without its challenges. Their faintness and distance make them incredibly difficult to observe, requiring astronomers to push the limits of technology and patience. What makes He-14240241 so special is its chemical composition. Like other ancient stars, it's almost entirely made up of hydrogen and helium, with only trace amounts of heavier elements. This lack of metals tells us that it formed from material that had not yet been enriched by the explosions of earlier stars. In essence, it's a pristine relic from a time when the universe was still in its infancy, offering a rare glimpse into the primordial gas clouds that gave birth to the first stars. But the story of He-14240241 doesn't end there. Its unique properties also provide clues about the processes that shaped the early universe. For instance, its low metal content suggests that it formed in an environment where star formation was still in its early stages. This helps scientists refine their models of how the first stars and galaxies came to be, shedding light on the transition from a dark, empty universe to one filled with light and structure. Studying stars like He-14240241 also helps us understand the timeline of the early universe. Its age, estimated to be around 13 billion years, places it among the oldest stars ever discovered. This means it formed not long after the Big Bang, providing a benchmark for when the first stars began to illuminate the cosmos. By analyzing its properties, astronomers can better estimate when the universe transitioned from a featureless void to one teeming with stars and galaxies. Despite the challenges of studying such ancient stars, He-142402441 continues to captivate scientists and stargazers alike. Its existence reminds us of the universe's incredible journey from its chaotic beginnings to the complex, beautiful structure we see today. As we turn our attention to the next star in our journey, we'll uncover even more secrets about the universe's earliest days and the stars that shaped its destiny. Now, let's take a closer look at the chemical fingerprint of He-142402441, a signature that holds the key to understanding the universe's earliest chapters. This ancient star's composition is like a cosmic time capsule, preserving the elements that existed in the primordial gas clouds from which it formed. Unlike younger stars, which are enriched with heavier elements forged in the hearts of earlier stellar generations, He-142402441 is almost entirely composed of hydrogen and helium, with only the faintest traces of metals. This stark simplicity is a direct window into the universe's infancy, a time before the first stars had exploded and scattered their heavier elements across the cosmos. The near absence of metals in He-142402441 is particularly significant. It tells us that this star formed from material that had not yet been touched by the nucleosynthesis processes of earlier stars. In other words, it's a pristine relic, untouched by the chemical evolution that would later shape the universe. This makes it an invaluable tool for scientists studying the conditions of the early universe. By analyzing its composition, astronomers can piece together what the universe was like before the first stars began to die and seed the cosmos with heavier elements. One of the most fascinating aspects of He-142402441's chemical fingerprint is what it reveals about the first generation of stars, often referred to as population 3 stars. These stars, which have never been directly observed, are thought to have been massive and short-lived, exploding as supernova and enriching the surrounding gas with the first heavy elements. The lack of these elements in He-142402441 suggests that it formed from gas that had not yet been polluted by these early supernovae. This provides crucial evidence for the existence of population 3 stars and helps scientists refine their models of how the first stars and galaxies came to be. But the story doesn't end there. The tiny amounts of heavier elements found in He-142402441 also offer clues about the processes that occurred in the early universe. For example, the presence of certain elements like lithium can help astronomers understand the conditions of the Big Bang itself. Lithium is one of the few elements produced in significant quantities during the Big Bang, and its abundance in ancient stars like He-142402441 can be compared to theoretical predictions, helping to test and refine our understanding of the universe's origins. Studying the chemical fingerprint of stars like He-142402441 also sheds light on the timeline of the early universe. By comparing its composition to other ancient stars, astronomers can piece together a more detailed picture of how and when the first stars formed, lived, and died. This helps us understand the transition from a dark, featureless universe to one filled with light and structure, a process that took place over billions of years but left its mark in the chemistry of stars like this one. As we continue to explore the mysteries of He-142402441, we're reminded of how much there is still to learn about the universe's earliest days. Each discovery brings us closer to understanding the forces that shaped the cosmos and the stars that illuminated its dark beginnings. And as we turn our attention to the next star in our journey, we'll uncover even more secrets about the universe's ancient past and the stars that continue to guide our understanding of it. Now, let's circle back to He-152300901, a star that continues to captivate astronomers with its ancient origins and the secrets it holds about the universe's timeline. This remarkable star, nestled in the halo of our Milky Way, is not just a relic of the past but a key to unlocking the chronology of the cosmos. Its age, estimated at around 13.2 billion years, places it among the oldest stars ever discovered, offering a glimpse into a time when the universe was still in its infancy. One of the most intriguing aspects of He-152300901 is how its age was determined. Unlike younger stars, whose ages can be estimated through their position on the Hertzsprung-Russell diagram, ancient stars like this one require more sophisticated methods. Scientists rely on a technique called radioactive dating, which involves measuring the decay of certain elements within the star. Specifically, they look at the ratios of uranium and thorium to stable elements like europium. These elements act as cosmic clocks, ticking away over billions of years and providing a way to measure the star's age with remarkable precision. The use of radioactive dating for He-152300901 has yielded fascinating insights. For instance, the star's uranium to thorium ratio suggests that it formed relatively soon after the Big Bang, during a period when the universe was still cooling and the first stars were beginning to ignite. This makes it a critical piece of the puzzle in understanding how and when the first structures in the universe began to form. By studying stars like He-152300901, astronomers can refine their models of the early universe, testing theories about the timeline of cosmic evolution. But the significance of He-152300901 goes beyond its age. Its chemical composition also provides clues about the environment in which it formed. Like other ancient stars, it is extremely metal-poor, with only trace amounts of elements heavier than helium. This suggests that it formed from gas that had not yet been enriched by the supernova of earlier stellar generations. In other words, it's a snapshot of the universe before the first stars had completed their life cycles and scattered heavier elements across the cosmos. What's particularly fascinating about He-152300901 is how it challenges our understanding of stellar formation in the early universe. Its existence suggests that even in the primordial gas clouds, there were pockets of material dense enough to collapse and form stars. This raises questions about the conditions that allowed these early stars to form and how they influenced the subsequent evolution of the universe. By studying stars like He-152300901, astronomers can piece together a more detailed picture of the processes that shaped the cosmos in its earliest days. As we continue to explore the mysteries of He-152300901, we're reminded of how much there is still to learn about the universe's ancient past. Each discovery brings us closer to understanding the forces that shaped the cosmos and the stars that illuminated its dark beginnings. And as we turn our attention to the next star in our journey, we'll uncover even more secrets about the universe's ancient past and the stars that continue to guide our understanding of it. As we reach the end of our journey through these 30 ancient stars, it's clear that each one holds a unique piece of the cosmic puzzle. From the Methuselah Star, which challenges our understanding of the universe's timeline, to He-152300901, whose radioactive dating offers a glimpse into the universe's infancy, these stars are more than just celestial objects, they are time capsules. They reveal the conditions of the early universe, the formation of the first stars, and the processes that shaped the cosmos as we know it today. What's truly remarkable is how these stars defy our expectations. Many of them are older than the universe itself, at least according to our current estimates. This paradox forces us to rethink our models of cosmic evolution and consider new possibilities. Were there stars that formed even before the Big Bang, or do our methods of dating need refinement? These questions remind us that the universe is far more mysterious and complex than we can imagine. The chemical fingerprints of these ancient stars also tell a story. Their metal-poor compositions suggest they formed from the primordial gas of the early universe, untouched by the heavy elements forged in later stellar generations. By studying them, we gain insights into the first moments of star formation and the conditions that allowed the universe to evolve into the rich, diverse cosmos we see today. But perhaps the most profound takeaway is how much we still have to learn. Each discovery raises new questions, pushing the boundaries of our knowledge and inspiring us to look deeper into the cosmos. These ancient stars are not just relics of the past, they are beacons guiding us toward a better understanding of the universe's origins and its ultimate fate. So, as we conclude this exploration, let's leave you with a question to ponder. What other secrets might the universe be hiding in its oldest stars? Could there be even more ancient stars waiting to be discovered, ones that could rewrite the story of our cosmic beginnings? The answers lie out there in the vast expanse of space, waiting for us to uncover them. If you're as fascinated by these mysteries as we are, don't forget to like, subscribe, and hit the notification bell to stay updated on our cosmic journeys. Until next time, keep looking up. The universe has so much more to reveal.